Good day to everyone. Today we are going to discuss part 3 of Module 5 for the subject CE 315. In this lecture, we are going to discuss the false position method, which is another method under the bracketing method in determining the roots of nonlinear equations. So for bracketing method, the false position method is an improvised version of the bisection method that we just have discussed in the previous lecture videos. So this is also known as the regula fallacy method, in which it is a trial and error technique in which we use a test or a false value for the variable, and we adjust the test value according to the outcome of our procedure. The only difference of the false position to bisection method is that the choice it makes in subdividing the interval at each iterations. So in bisection method, we divide the values that we have computed by 2 or by half for every iterations. In here, we have a different way of solving for the brackets or the limits of our solutions or of our iterations. So in here, false position method now will converge faster compared to the bisection method. So the procedure for false position method would also be the same as for bisection method, wherein we start with our initial guess for the interval xl and xu, and then we compute now for the functions of xl and xu, in which the 2 points taken from the functions would now be connected using a straight line. So they'll be forming a straight line. The estimated root xr now is the x value where the straight line crosses the x-axis. So this is a figure or a graphical representation of how the false position would work. So we have now our initial guess xl and xu. Take the function, and then when you connect it by a straight line, so fxl function of xu. So the point wherein the line connecting the two functions intersects will be our representation of the value of the function of our estimated root. So from there, we'll be able to identify now the new limits for our new iterations. So same procedure, function of xl, function of xu, which was the first root computed. So intersection to the x-axis will be your new xr until you arrive at the true value or the true solution of your nonlinear equation. Okay? So the straight line joining the 2 points, we have xl and fxl, and xu, fxu will give us the following equation. Okay? So this is for the function. So this is the slope of the line connecting fxl and fxu. Okay? So with that, since the line intersects the x-axis at the root xr, so for x, this now is xr, and its equivalent y-intercept is equal to 0. So the previous equation can be simplified into xr minus xu equal to negative fxu times xu minus xl divided by the function of xu minus function of xl. So nag-cross multiply lang tayo, and then we change x to xr and y to 0. From there, rearranging this equation now will yield the equation or the formula for the false position method in determining now the root or estimated root xr. So xr now is simply equal to, transpose this value, xu minus fxu times xl minus xu divided by function of xl minus function of xu. So, pinasok ko lang itong negative dito sa loob para kaya nagkaroon ng interchange doon sa ating equation. So, basically, for bisection method, yung XOR natin is simply XL plus XU divided by 2. Sa false position method, this is now our working equation for the value of our XR. The following steps or procedures are what we are going to follow in computing for the roots using false position method. So for step 1, we choose your initial guesses for the lower and upper limits of the brackets such that the function will have opposite signs over the interval. So meaning our guess should be between, so XL should be less than or equal to the true solution or the true root of the equation and should be less than or equal to XU. Next, step 2, after giving the initial guess, we estimate now the XR or the root of the equation using the formula for false position method. Once you have computed for XR, step 3 is to identify the subintervals or the new limits in which the root lie. So we check now the conditions. If the product of the function of XL times the product times the function of XR is less than 0, then it means that the root will lie between your lower limit and the computed estimated root XR. If the product between the function of XL and the function of XR is greater than 0, then your root will lie between XU and XR. And if the product of the functions of XL and XR is equal to 0, then it means that the computed XR is our true solution or the true root of the equation. So if you can see, we have the same conditions as we use for bisection method. So the only difference here is the equation for XR. Okay? So next, once you have checked for the conditions and have identified which is the subinterval or the new limit for your next iteration, we move to step 4, which is to calculate the absolute relative approximate error of our values, which is given by EA or epsilon E equal to your new root minus the old root divided by the new root times 100%. And then from there, we now compare this to the value of our stopping error or our stopping criterion. Okay? So kung hindi given yung stopping criterion, then we could simply use the conditions under step 3. Okay? So termination will depend on either step 3 here, if the function or the product is equal to 0, or if we have achieved the condition that the error approximate is less than the stopping criteria. So to understand better false position method, let us solve some example. So for the given equation, the function of x is equal to negative 3x cubed plus 19x squared minus 20x minus 13. We now determine its first root by the false position method using initial guesses for the xl equal to negative 1 and xu equal to 0 with the stopping criterion e sub s equal to 1%. So for our solution, for our first iteration, we are given xl equal to negative 1 and xu is equal to 0. So in here, we now solve for our functions of our limits or of our brackets. So for fxl, substituting negative 1 in the given equation, we get 29. Substituting 0 in the equation, we get function of xu equal to negative 13. And then, after that, we compute now for our estimated root using xu and the functions computed. So substituting our values, we have now 0 minus negative 13 times negative 1 minus 0 divided by 29 minus 13, giving us a value of XR, which is negative 0.3095. Okay, so with that, we compute for the function of XR, which will give us negative 4.9010. Okay, so we check now the product of the function XL and function XR. That's 29 times negative 4.901. Okay, so it's a negative value, so meaning it is less than 0. So therefore, our limit or new subinterval, new interval is equal to XL negative 1, and XR now becomes our new upper limit or upper X value. And then we solve for your EA. Substitute now XR, but we do not have a previous XR, so this one will just be a blank, or we leave this first. So we move now to our second iteration. So our limit lower is negative 1 with equivalent function equal to 29. Our new XU is negative 3 point or 0.3095. Equivalent function is negative 4.9010. So we compute for our XR. And XR now, substituting the values of XU, XL, and the functions, will give us a value of negative 0.4093. And computing for its function, it's equal to negative 1.4253. Okay, so looking back, XL times FXR, positive times negative is a negative value, so it's less than 0. So our new subinterval or the new limit for our next iteration will be negative 1 and XR. So from here, we can now compute our approximate error since we have our previous XR and our new XR, which will give us 24.30. So comparing our EA to our stopping criterion, it is greater than 1, the stopping criterion, therefore, we have to continue with our iteration. Okay, next, our new upper limit is negative 0.4093. So we compute for XR, which will give us a value of negative 0.4370. Compute for the function by substituting XR in the given equation, we get negative 0.3812. And then computing now FXL and FXR, which will yield a negative value. So therefore, it is less than 0. Therefore, our new limit for the next iteration will be between negative 1 and negative 0.3812. Then we check now our approximate error using our previous XR and our new XR. So we have 6.34%, which is still greater than our stopping criterion. Therefore, we continue with the next iteration. So for our fourth iteration, given XL and XU, negative 1 and negative 0.4307, we now compute for XR, the new XR, which is equal to negative 0.4443, which will yield a function of the XR equal to negative 0.1002. So, checking now, product of FXL and FXR is negative, so it's less than 0. So our new limit for the bracket for our next iteration will be negative 1 and negative 0.1002. And from there, we compute now our approximate error, which is 1.64%, which is still greater than 1%, which is our stopping criterion, then we continue with our fifth iteration. So for the fifth iteration, XL is -1, XU is -0.4443. Compute for XR by substituting now the values of XL and XU and the functions. So we get now XR equal to -0.4462. Compute now, substitute this in the equation to compute for its function, which is -0.0267. Computing for XL, function of XL times function of XR will give us a value less than 0. So meaning our new lower limit is -1 and upper limit is -0.0267. And computing for our approximate error, it will be 0.43%, which is now less than the given stopping criterion, meaning we can now terminate with our iterations or our computations. So we have already found our estimated root, which is 0.4462 negative. Okay? So if we are not given the stopping criterion, then what we will use to consider if we have to terminate is the product of fxl and fxr should be equal to 0. But if we are given the stopping criterion, then we have to also consider the relationship of the approximate error and the stopping criterion. Okay? So since we have achieved already the condition for EA and ES, we can terminate. But if the ES is not given, then we could continue with our next iteration using -1 and -0.0267. Okay, so as a summary, for our first problem, we could do it in a tabular form. So we have the iteration, your lower limit, upper limit, your estimated root for that iteration, the function of XL, function of XU, function of XR, the product of the function of XL and XR, and the approximate error in percent. So for your first iteration, you have -1 and 0. So we have computed XR here. Computed is negative, so meaning less than 0. So I have to continue. Okay, so just substitute this tabular formula. Okay, so XR, since it's negative, the product of XL and XR, therefore the XR becomes your new XU. Same for the next iteration. This is negative. So therefore, our XU is now the previous XR. Again, negative yung product. So XR now becomes the new XU, the next iteration. Okay. Then we have for the fifth iteration, so less than na stopping criteria. Okay, so you can present your final answers in a tabular form so that we will have a more presentable solution. Okay, so if you want to continue, you can continue with the sixth iteration with -1, then -4462, then compute for XR, function of XL, FXU, FXR, the product, and the approximate error. Okay? So for approximate root, this is achieved at the fifth iteration, which is -0.4462 with a relative approximate error of 0.45.